Let's define vertex. Well, a vertex is a point. That is, and I'm going to put this in parentheses because it's not always the case, potentially, this is not the technical definition, connected to other points. It's that simple. So here it is. In our context, it was a city. So A was connected to B, and A was connected to C, and A was not connected to D, but it had the potential to be. Okay? An edge is a connection between vertices, that's plural for vertex. Define adjacent vertices. These are vertices that are connected. With an edge, which I almost misspelled. Edge, there we go. And define degree. Okay, so I think we already can find degree, but let's define it. And that would be like, well, A is 3 and B is 2. And I think it would be the number of, well, red lines. So we'll call them edges. So this is the number of edges coming from, that's important, a vertex. Okay, I want to take this opportunity and talk about degree within the context of an adjacency matrix. So check this out. This is a good way to kind of spot check your adjacency matrix and make sure that there are no glaring errors. This isn't the final proofread of it, but it's a good way of doing it. So check this out. The degree of A is 3, right? So B, C, and E. So, I mean, yeah, B, C, and E. But basically, if the degree of A is 3, then this row is going to have 1, 2, 3. And the degree of B is 2. So 1, 2. That's just a good way to quickly check and see what we have. All right, let's flip the paper over. Let's do another example very quickly. Alphabet Airlines has another set of cities that they service. They are as follows. Los Angeles, that would be an L, connects to Minneapolis, Nashville, Oklahoma City, and Phoenix. Again, Alphabet Airlines, so convenient in the way they do things, and let's just go ahead and connect these things. So Los Angeles connects to Minneapolis, Los Angeles connects to Nashville, I almost said New Orleans, Oklahoma City, and Phoenix. All right, Minneapolis connects to Phoenix, so Minneapolis connects to Phoenix. Okay, again, that intersection, it means nothing. All I care about is that M and P are connected. Nashville connects to Phoenix. So we create the graph that represents the situation, and we're going to write the adjacency matrix. So we're going to go ahead and do that, and this is going to be 5 cities. So it's going to be a 5 by 5 matrix. LMNOP and LMNOP. All right, I'm not going to put my rows in this one. I'm not going to put the lines in. So L is connected not to itself, but L is connected to M, N, O, and P. M, N, O, P. M is not connected to itself. M to M is not a thing. N to N is not a thing. O to O is not a thing. P to P is not a thing, okay? All right, but M is connected to L. M is connected to P, and nothing else. N is connected to L. N is connected to P, and nothing else. O is connected to L. O is not connected to anything else, including itself. P is connected to L, M, and N, but not O. There we go. All right, I want to take this opportunity to make one more observation, and the observation is this. In this particular type of graph, and we're going to have a different one here in a minute that has arrows. We'll talk about what that means, but in this particular type of graph, the row matches the column. Okay, so let's just read it. 0, 1, 1, 1, 1. Now let's read down. 0, 1, 1, 1, 1. Cool, huh? Okay, so let's just pick let's pick n. The n row and the n column. 1, 0, 0, 0, 1. Same thing here. 1, 0, 0, 0, 1. That only works if we don't have arrows. If it does have arrows, things change a little bit. We're going to get to that in a few minutes.